Information theory is a branch of applied mathematics, electrical engineering, and computer science involving the quantification of information. Information theory was developed by Claude E. Shannon to find fundamental limits on signal processing operations such as compressing data and on reliably storing and communicating data. Since its inception, based on a landmark 1948 paper by Shannon, it has broadened to find applications in many other areas, including statistical inference, natural language processing, cryptography, neurobiology, the evolution and function of molecular codes, model selection in ecology, thermal physics, quantum computing, linguistics, plagiarism detection, pattern recognition, anomaly detection and other forms of data analysis. A key measure in information theory is entropy. Entropy quantifies the uncertainty involved in predicting the value of a random variable. For example, specifying the outcome of a fair coin flip provides less information than specifying the outcome from a roll of a die. Some other important measures in information theory are mutual information, channel capacity and relative entropy. Applications of fundamental topics of information theory include lossless data compression, lossy data compression, and channel coding. The field is at the intersection of mathematics, statistics, computer science, physics, neurobiology, and electrical engineering. Its impact has been crucial to the success of the Voyager missions to deep space, the invention of the compact disc, the feasibility of mobile phones, the development of the Internet, the study of linguistics and of human perception, the understanding of black holes, and numerous other fields. Important subfields of information theory are source coding, channel coding, algorithmic complexity theory, algorithmic information theory, information theoretic security, and measures of information. Overview. Information theory studies the transmission, processing, utilization, and extraction of information. Abstractly, information can be thought of as the resolution of uncertainty. In the case of communication of information over a noisy channel, this abstract concept was made concrete in 1948 by Claude Shannon in A Mathematical Theory of Communication, in which information is thought of as a set of possible messages, where the goal is to send these messages over a noisy channel, and then to have the receiver reconstruct the message with low probability of error, in spite of the channel noise. Shannon's main result, the noisy channel coding theorem, showed that, in the limit of many channel uses, the rate of information that is asymptotically achievable is equal to the channel capacity, a quantity dependent merely on the statistics of the channel over which the messages are sent. Information theory is closely associated with a collection of pure and applied disciplines that have been investigated and reduced to engineering practice under a variety of rubrics throughout the world over the past half-century or more. Adaptive systems, anticipatory systems, artificial intelligence, complex systems, complexity science, cybernetics, informatics, machine learning, along with systems sciences of many descriptions. Information theory is a broad and deep mathematical theory, with equally broad and deep applications, amongst which is the vital field of coding theory. Coding theory is concerned with finding explicit methods, called codes, for increasing the efficiency and reducing the error rate of data communication over noisy channels to near the channel capacity. These codes can be roughly subdivided into data compression and error correction techniques. In the latter case, it took many years to find the methods Shannon's work proved were possible. A third class of information theory codes are cryptographic algorithms. Concepts, methods and results from coding theory and information theory are widely used in cryptography and cryptanalysis. See the article Ban for a historical application. Information theory is also used in information retrieval, intelligence gathering, gambling, statistics, and even in musical composition. Historical background. The landmark event that established the discipline of information theory, and brought it to immediate worldwide attention, was the publication of Claude E. Shannon's classic paper, A Theory of Communication, in the Bell System Technical Journal in July and October 1948. Prior to this paper, limited information theoretic ideas had been developed at Bell Labs, all implicitly assuming events of equal probability. Harry Nyquist's 1924 paper, Certain Factors Affecting Telegraph Speed, contains a theoretical section quantifying intelligence, and the line speed at which it can be transmitted by a communication system, giving the relation W equals K log M, where W is the speed of transmission of intelligence, M is the number of different voltage levels to choose from at each time step, and K is a constant. Ralph Hartley's 1928 paper, Transmission of Information, uses the word information as a measurable quantity, reflecting the receiver's ability to distinguish one sequence of symbols from any other, thus quantifying information as H equals log S, N equals N log S, where S was the number of possible symbols, and N the number of symbols in a transmission. The unit of information was therefore the decimal digit, much later renamed the Hartley in his honor as a unit or scale or measure of information. Alan Turing in 1940 used similar ideas as part of the statistical analysis of the breaking of the German Second World War Enigma ciphers. Much of the mathematics behind information theory with events of different probabilities were developed for the field of thermodynamics by Ludwig Boltzmann and J. Willard Gibbs. Connections between information theoretic entropy and thermodynamic entropy, including the important contributions by Rolf Landauer in the 1960s, are explored in Entropy in Thermodynamics and Information Theory. In Shannon's revolutionary and groundbreaking paper, the work for which had been substantially completed at Bell Labs by the end of 1944, Shannon for the first time introduced the qualitative and quantitative model of communication as a statistical process underlying information theory, opening with the assertion that the fundamental problem of communication is that of reproducing at one point, either exactly or approximately, a message selected at another point. With it came the ideas of the information entropy and redundancy of a source, and its relevance through the source coding theorem, the mutual information, and the channel capacity of a noisy channel, including the promise of perfect loss-free communication given by the noisy channel coding theorem. The practical result of the Shannon-Hartley law for the channel capacity of a Gaussian channel, as well as the bit, a new way of seeing the most fundamental unit of information. Historical description of entropy. Although this terminology is no longer in use, Shannon's original description is as follows. When a set of symbols is big enough to accurately characterize the probability of each symbol, the Shannon entropy H in bits per symbol, or entropy per symbol, is where pi is the probability of a particular symbol I occurring, and counter is the number of times it occurs in the data that is n symbols long. This equation is bits per symbol because it is in a logarithm of base 2. Normalize entropy in units of entropy per symbol from a data source ranges from 0 to 1 when the logarithm base is n, i.e., when multiplied by lane if h was calculated in base 2 logarithm. Therefore an h calculated with log 2 is in units of entropy per symbol, as well as bits per symbol, if there were only 2 symbols in the data. The extensive entropy of a message, file, source, or other data is S equals N asterisk H. In keeping with Boltzmann's H theorem, S equals KBNH for physical entropy that Claude Shannon's 1948 paper cited as analogous to his information entropy. Shannon's H is usually called entropy because that is what Shannon called it, but he always stated its units were entropy per symbol, bits per symbol, or information per symbol. This shows H is analogous to physics-intensive entropy S0, that is on a per mole or per kilogram basis, which is different from the more common extensive entropy S. Section 1.6 of Shannon's paper refers to H as the entropy of the set of probabilities, normalized to one symbol. It is instructive to see H values in bits per symbol for several examples of short messages by using an online entropy calculator. http://www.shannonentropy.net mark.pl/http://planetcalc.com/2476/h equals 04 and 11111. H equals 1 for AB, ABAB, 0011, and 011010101010101. H equals 1.58 for ABC, 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 and RRBAB 2222. H equals 2 for ABCD, and AABBCCDD. The entropy in each of the above is S equals H asterisk n, if the probabilities of the symbols in each is representative of the source of each string. Quantities of information. Information theory is based on probability theory and statistics. Information theory often concerns itself with measures of information of the distributions associated with random variables. Important quantities of information are entropy, a measure of information in a single random variable, and mutual information, a measure of information in common between two random variables. The former quantity is a property of the probability distribution of a random variable and gives a limit on the rate at which data generated by independent samples with the given distribution can be reliably compressed. The latter is a property of the joint distribution of two random variables, and is the maximum rate of reliable communication across a noisy channel in the limit of long block lengths, when the channel statistics are determined by the joint distribution. The choice of logarithmic base in the following formulae determines the unit of information entropy that is used. A common unit of information is the bit, based on the binary logarithm. Other units include the nat, which is based on the natural logarithm, and the Hartley, which is based on the common logarithm. In what follows, an expression of the form p log p is considered by convention to be equal to 0 whenever p equals 0. This is justified because for any logarithmic base entropy, the entropy h of a discrete random variable x intuitively is a measure of the amount of uncertainty associated with the value of x when only its distribution is known. So, for example, if the distribution associated with a random variable was a constant distribution, then entropy is minimal, and equal to 0. Furthermore, in the case of a distribution restricted to take on a finite number of values, entropy is maximized with a uniform distribution over the values that the distribution takes on. Suppose one transmits 1000 bits. If the value of each of these bits is known to the receiver ahead of transmission, it is clear that no information is transmitted. If, however, each bit is independently equally likely to be 0 or 1, 1000 Shannons of information have been transmitted. Between these two extremes, information can be quantified as follows. If is the set of all messages x1, xn, that x could be, and p is the probability of some, then the entropy h of x is defined. Is the self-information, which is the entropy contribution of an individual message, and x is the expected value. A property of entropy is that it is maximized when all the messages in the message space are equiprobable p equals 1, n, i.e., most unpredictable, in which case h equals log n. The special case of information entropy for a random variable with two outcomes is the binary entropy function, usually taken to their logarithmic base 2, thus having the Shannon as unit. Joint entropy. The joint entropy of two discrete random variables x and y is merely the entropy of their pairing. This implies that if x and y are independent, then their joint entropy is the sum of their individual entropies. For example, if represents the position of a chess piece, x the row and y the column, then the joint entropy of the row of the piece and the column of the piece will be the entropy of the position of the piece. Despite similar notation, joint entropy should not be confused with cross-entropy. Conditional entropy. The conditional entropy or conditional uncertainty of X given random variable Y is the average conditional entropy over Y. Because entropy can be conditioned on a random variable or on that random variable being a certain value, care should be taken not to confuse these two definitions of conditional entropy, the former of which is in more common use. A basic property of this form of conditional entropy is that mutual information measures the amount of information that can be obtained about one random variable by observing another. It is important in communication where it can be used to maximize the amount of information shared between sent and received signals. The mutual information of X relative to Y is given by where Si is the point Y's mutual information. A basic property of the mutual information is that is, knowing Y, we can save an average of I bits in encoding X compared to not knowing Y. Mutual information is symmetric. Mutual information can be expressed as the average Kullback-Leibler divergence between the posterior probability distribution of X given the value of Y and the prior distribution on X. In other words, this is a measure of how much, on the average, the probability distribution on X will change if we are given the value of Y. This is often recalculated as the divergence from the product of the marginal distributions to the actual joint distribution. Mutual information is closely related to the log likelihood ratio test in the context of contingency tables and the multinomial distribution and to Pearson's chi-2 test. Mutual information can be considered a statistic for assessing independence between a pair of variables, and has a well-specified asymptotic distribution. Kullback-Leibler divergence. The Kullback-Leibler divergence is a way of comparing two distributions, a true probability distribution P, and an arbitrary probability distribution Q. If we compress data in a manner that assumes Q is the distribution underlying some data, when, in reality, P is the correct distribution, the Kullback-Leibler divergence is the number of average additional bits per datum necessary for compression. It is thus defined, although it is sometimes used as a distance metric. KL divergence is not a true metric since it is not symmetric and does not satisfy the triangle inequality. Another interpretation of the KL divergence is the unnecessary surprise introduced by a prior from the truth. Suppose a number X is about to be drawn randomly from a discrete set with probability distribution P. If Alice knows the true distribution P, while Bob believes that the distribution is Q, then Bob will be more surprised than Alice, on average, upon seeing the value of X. The KL divergence is the expected value of Bob's surprisal minus Alice's surprisal, measured in bits if the log is in base 2. In this way, the extent to which Bob's prior is wrong can be quantified in terms of how unnecessarily surprised it's expected to make him. Other quantities. Other important information theoretic quantities include acute NYI entropy, differential entropy, and the conditional mutual information.